Hi, in this video, I'm taking apart the components from my previous project, measuring everything, and pretty much breaking the whole thing. But there is an important lesson in all of this, so stick with me until the end. In the previous episode, I programmed the Arduino to send commands to the AD9830 module so it could generate different signals for us. The problem was that the module's output, especially when generating sine or triangle waves, was really weak. So to get a stronger and adjustable output amplitude, I turned to operational amplifiers. After several tests and simulations, I decided to use the LM830 IC. This setup not only amplifies the signal but also lets me adjust the DC level or output offset. The LM833 is a dual-channel op-amp. The first channel amplifies the signal and the second channel, which works as a summing amplifier, adds the amplified signal to the circuit's DC supply voltage. Here you can see the simulation of the circuit. The problem was that the LM830T couldn't provide the gain I needed all the way up to 12 MHz. To get the actual usable bandwidth, you have to divide the value in the datasheet by the amplified gain. And with the gain I wanted, it simply wasn't enough. So I found an op-amp with the 300 MHz bandwidth. But since it was a single channel IC, I needed two of them. One for the amplifier stage and one for the summing stage. That meant I had to redesign the PCB as well. I ordered the chips, updated the PCB design, and sent it out for manufacturing. The PCB took a bit of time to arrive. Meanwhile, I designed the front panel of the device in Photoshop, which required some very precise measurements. Finally, the new PCB arrived and I finished assembling all the components. Just like before, I connected the output to an LED for a quick test. But this time the LED stayed on constantly, and turning the knobs didn't change anything. On top of that, the second IC was getting extremely hot while the first one stayed cold. That was a clear sign something was wrong. I desoldered the ICs to test them and sure enough, both were damaged. The reason is that these high frequency op-amps are very sensitive, and you can't use large resistor values with them. You have to use the small, specific resistor values recommended in a datasheet. That means we can't have adjustable gain the way I originally planned. So at this point, continuing with the project wouldn't really make sense. The next day, I restored the PCB design back to the original version and decided to set the gain so that I'd have about 2 MHz of bandwidth. I also revised the goal of the project, to build a signal generator that could output signals from 1 Hz up to 1 MHz. This signal generator has two knobs for adjusting the output amplitude, one knob for controlling the frequency and multiplier, and a selector switch for choosing the waveform. To check the output waveform, I borrowed my friend's oscilloscope, but the signal looked really strange. The amplitude and offset knobs were working, but the waveform itself didn't make sense. When I got home, I built a simple oscilloscope using just 10 resistors and an Arduino. And once again, the waveform looked weird. That's when I realized the issue was actually in the code I had written. I fixed the software and yes, everything started working perfectly. So in this video, not only did I finish building the signal generator, but I also ended up making a basic oscilloscope. That definitely deserves a like. Thanks so much for watching.